to get out of here at a decent time because I know Chem 121 is coming in right after us today, so we can't really go over time. All right, so welcome to Unit 3 review. Hopefully you guys can use that. We're just going to go through and do what we've done the last couple of reviews. We'll go problem by problem on the practice problems that are posted up on D12. And if there's one you want to see, just say yes. If nobody says anything, we'll move on to the next one. All right. So number one. Yes. Okay. So for number one, it says when a weak acid is titrated in a strong base, the pH, or titrated with a strong base, the pH initially does what? And so if we look at the titration curve with volume down here and pH here, since we're titrating a weak acid with a strong base, it's going to have a fairly low pH when we start. And initially the pH increases pretty quickly, and then it levels off, and then it goes shooting up near the equivalence point. And the reason it does this, you can see it's got a pretty good slope right here, and then the slope of increase mellows off a little bit right there. As you, when you start, you have nothing more than weak acid, and you're adding that strong base. And so as you add the strong base, the pH starts to go up pretty quickly. However, as you're adding that strong base, it's reacting with that weak acid, and it starts to create, from that weak acid, it starts to create that weak acid's conjugate base. And as the amount of conjugate base increases, eventually you get to a ratio of the original weak acid and the weak base that's being produced. It begins to create a buffer solution. When they create that buffer solution, then the pH increase starts to be resisted, and the slope starts to mellow off a little bit. It happens pretty quick depending on the solution, but you do have an initial fairly quick rise in pH, and then it levels off a little bit because you're creating a buffer solution while you titrate. Okay, hopefully that made sense. Any questions on that one? Yeah?
Would it be exactly the same if it was the opposite?
So if you're titrating a weak base with a strong acid, yeah, then the pH would decrease fairly rapidly and then mellow out a little bit. Yeah. All right. Number two. Yes. So for number two, as you go through there, there's 4 different choices of acids and salts. All of the salts have group 1A metal with them, so those are all going to be a source of anion that is related to the acid that's given. It wants to know which of these pairs will be a buffer solution. You've got to remember what our definition of a buffer solution is. Okay, it's a weak acid or weak base and its conjugate. Okay, so we have to have a weak acid or a weak base as part of that buffer, and then its conjugate. So if we go through, if we look at B, C, and D, we see for the acids in there, they've got HI, HBr, and HCl. Those are all strong acids, and they cannot set up a buffer situation because they don't have an equilibrium with their conjugate. Okay? Because they're strong acids, they dissociate completely, and there's no equilibrium. A, however, HF is a weak acid, and it also contains CSF, and so that will dissociate into just F-. So you'll have HF and F-, a weak acid and its conjugate weak base, and that will make that solution a buffer. Okay, questions at all on that one? Okay. Number 3. So number 3 should be C. I corrected that. If you printed off the handout fairly early, it may have said B. I don't know why I put B down there, just typos. I was typing in the key. But it should be C. Does anybody still need to see that one? So we have hydrofluoric acid, HF. So if we have HF, what we need to make a buffer solution is a source of its conjugate weak base, which would be F-. And NaF, since that's a sodium salt, that will dissociate in water to Na+, which would be a spectator, plus F minus, and so now we have HF and F minus, so that will set up a buffer solution. Yeah?
How do you identify a spectator?
Your group 1A, group 1A metals, your things like nitrates, things that form no precipitates at all, they never take place in any reaction we see. All right. Number 4. Yeah, expected that one. So number 4 says the pH of a solution prepared by dissolving 0.35 moles of methylamine hydrochloride in 1 liter of 1.1 methylamine is blank. And we're given the KB for methylamine. So since we're given the KB for methylamine, let's just go ahead and write out the equilibrium reaction for methylamine based on that KB. And I told my classes today, so if you see a KB for a reaction, remember that is an equilibrium constant, and it's for a very specific reaction, KBs and KAs. They are the reaction of that acid or base with water. Okay, that's what the equilibrium constant is always for. So if we're looking at methylamine, the KB for methylamine, that's going to be CH3NH2, and since we have a KB, it's going to be acting as a base. So we're going to react that with water, and that's going to give us CH3NH3 plus OH minus. Now, I actually don't do much with that, and that's okay. It does help set up our Henderson-Hasselbalch equation if we, in fact, are going to need it. It also helps identify the fact that methylamine hydrochloride is the conjugate base of the methylamine. The chloride is just going to go floating off into solution there as a spectator. Well, because if this is a base, it's going to act, what do bases do? They take H's away. So it's going to take an H away from water and leave us with OH minus. All right. So we just have a buffer solution. We're not doing anything to this solution. And so what we want to do is we have just 1 liter of solution. We've got 0.35 moles of the methylamine hydrochloride. That's just going to dissolve in and become 0.35 molar because we're going to have 0.35 moles in the 1 liter solution. So that's going to be 0.35 molar. And if we look at our POH here, that would be equal to the PKB plus. And when we do our Henderson-Hasselbalch equation, it's always our product over our reactant. And it's the product of and the reactant of the equilibrium reaction from the K. Okay, it's not when you're reacting it with something, it's that equilibrium reaction for the K. And so we're going to have log of CH3NH3 plus, forgot that little plus there, over CH3NH2. Okay, so now we can do that when we get our POH. Our PKB, if you work that one out, take the negative log, you get 3.36 plus log of 0.35 over 1.1. Those values were given to us in the problem, and you get a POH of 2.86, and then you subtract that from 14 to get a pH, and you get a pH of 11.14. Any questions on any part of that I did? I'm sorry, say it again. Mm-hmm. Well, it is. The hydro is the acid part. The chloride just comes off as a spectator. Yeah. Yep. Yep.
You said that
you have to use the equilibrium equation to set up the Henderson-Hasselbalch because that's what it's derived from. It's derived from that ice box from the equilibrium. Yep. Anything else? Okay. Number 5. Yes. Okay, so we have Ka of acetic acid is 1.8 times 10 to the minus 5. The pH of a buffer prepared by combining 50 milliliters of 0.25 molar potassium acetate and 50 milliliters of 1 molar acetic acid is what? So let's just set up our equilibrium reaction there. Since we're given the K of acetic acid, I'm just going to abbreviate that as HAC because I don't feel like writing out the whole formula for acetic acid. So because it's a Ka, it's going to be the acetic acid with water. And that's going to give us H3O plus our acetate on it. Okay, because we're changing our volumes here, we're going to want to use millimoles here. Just because anytime that volume changes, you've got to be really careful. You can't just use concentrations because those are going to change on you. So we want to use millimoles here because millimoles don't change regardless of your final volume. So let's set up our Henderson-Hasselbalch equation because all we have is a buffer solution. We haven't added anything to it. So we're going to have pH is equal to pKa plus log, and again it's going to be concentration of AC minus, that's my product for my buffer, over HAC, it's my reactant for my buffer. Okay. So for my AC minus, my acetate ion, that's going to be, what do we have? We have 50 milliliters times 0.25 molar. And so that's going to be equal to 12.5 millimoles. And for my acetic acid, I have 50 milliliters times 1 molar. And so that's equal to 50 millimoles. And so I can plug those values in. We get pH is equal to our pKa. So if we take the negative log of our Ka, we're going to get 4.74 plus the log of my acetate millimoles, 12.5 over my acetate millimoles, 50. And when we work that one out, we get 4.14. Now on this one, this is kind of a weird problem. We have them like this in class today. Because we use the exact same volumes of the acid and the base there, even if we put in our original concentrations of 0.25 and 1, we still would have got the same answer. But that's only because the buffer used the same volume of each of those. If those volumes had been different at all, then that wouldn't work. Because you always want to make sure you account for the different number of millimoles there. Okay, questions at all on that one? Yeah?
About 4.35 is the actual value in the half flow. Is that pretty big difference?
I'm sorry, what was that again?
Like the actual value, when you do that, you do all the statistics for the pKa, it's like 4.35. It's like...
I don't, what are you talking about?
Well, the pH.
What about the pH? If you do 12.5 over 50 and take the log,
yeah,
and then you add it, I get 4.14, I think. You guys get a different answer?
yeah, it's like close, but it's off by 2 tenths.
Well, that's huge.
Yeah.
Did anybody else get that? I could have screwed up when I wrote this one up because I had to change the values. So they're getting 4.14. So I'm not sure what you're doing there. I can take a quick look. If you do 12.5. Yeah, I mean the log of 12.5 over 50 is 0.6, negative 0.6. So that's going to be 4.14. So, yeah. All right. Anything else on that one? Okay. Let's see. Number 6. Yes. Okay, so 6 says what change will be caused by by addition of a small amount of HCl to a solution containing fluoride ions and hydrogen fluoride. Okay. Well, if we have fluoride ions and hydrogen fluoride, then we have a buffer solution. We can just set that one up like this. And we don't have to do this, but it helps some people. So that's going to be H3O plus F minus. So there's the equilibrium of the HF with water there. Okay. Now, if I add HCl, of course, is an acid. And what do acids like to react with? Bases. What's the base in this equilibrium, in this buffer? It's the F minus. So HCl is going to react with F minus. Okay, and it's going to do so in 100% reaction because it's a strong acid, and that's going to make HF and Cl minus. So if we look at what's happening here, what happens to the amount of F minus as it reacts with HCl? It's going to go down. And then what happens when that reaction happens to HF? HF's going to go up because it's now being made. And so the correct answer there is E. Concentration of fluoride ion will decrease because it's reacting with the HCl. And concentration of HF will increase because it's being made by that reaction. Questions at all on that? That's a hard thinking problem. You got to really think about that. All right. Turn this page real quick. All right, number 7. I'm not sure there's any I'm not doing tonight. Number 7, consider a solution containing 0.1 molar fluoride ions and 0.126 molar hydrogen fluoride. I seem to have been on a hydrogen fluoride kick when I was writing this. The concentration of hydrogen fluoride after addition of 5 milliliters of 0.01 molar HCl to 25 milliliters of buffer solution is what? Okay, so once again we've got our we can look at our buffer reaction. We've got HF plus H2O goes to F minus plus H3O plus. Okay, so just like in the problem before, now we're actually going to add some HCl to this. And that HCl is going to react with the F minus, just like we said in the previous problem. So we're going to have HCl plus F minus, and that's going to go to HF plus Cl minus. And now we're looking at the how much. So we're going to icebox this one. Okay. And because we are doing a reaction where we're changing volumes, we want to use millimoles here. That keeps everything kind of straight. And so to find millimoles, we just take the volume in milliliters times the molarity. So for the H plus, we get 5 times 0.01. So that's 0.05. For the fluoride ion, we have 0.1 times 25, because we have 25 milliliters of the buffer. So that's 2.50. And for the HF, we have 0.126 times 25, and that gives us 3.15. Okay, the HCl and the F minus are going to react until something's used up. That's going to be the HCl. So minus 0.05 minus 0.05 for the F minus, because it reacts in a 1-to-1. And the HF is going to get 0.05 because a little bit of it's going to be made. And so at the end of that, we're going to have no HCl left. We're going to have 2.45 millimoles of F minus left and 3.20 millimoles of the HF left. Now, a lot of people came in because they couldn't figure out why their answer was nowhere near what they were getting, or for any of the choices in there. It's because they were going through and calculating the pH. That's not what the problem is asking for. The problem is asking you to calculate the new concentration of HF at that point. And so to get the concentration of HF, we're just going to take the millimoles of that, 3.20, divided by the new volume in milliliters, and we had 25 milliliters of buffer solution. We added 5 milliliters of acid, so now we have a solution of 30 milliliters. Put on some units here. And when we work that out, we get 0.107 molar for our concentration. So we just want to make sure you read the problem and know what it's asking for. Any questions there? If you did that problem, went through it, found a pH, and then realized, oh, I wasn't even asking for that, don't feel bad, because I did it too. So used to doing that with these problems. Okay, number 8. Yes. So for number 8, now number 8 had a correction as well on the sheet. I think it originally said A, it should have been E. So 0.51 is the answer. So let's see. So we're looking for the pH of 100 milliliters of 1 molar HCl solution after 30 milliliters of 2 molar NaOH solution is added. So we'll go number 8 here. So we have a strong acid, strong base. Remember, that's our simplest calculation for these. So that's just going to make H2O plus NaCl. And what makes these so much easier than the other titrations where we're adding the solutions together is because there's no equilibrium involved here. It's just they react and then they're done. So we want to do this in terms of millimoles, so we're going to icebox that. Okay, so we have 100 millimoles of HCl. We have 60 millimoles of NaOH. Okay, we don't really care about the H2O or the NaCl. So they're going to go till something runs out, so minus 60, minus 60. So we're going to have 40 millimoles of HCl left and no NaOH there. And then we get our new concentration of HCl. Remember, that's going to be equal to the concentration of hydronium ion because it's a strong acid. And so that's going to be equal to 40 over 130, because I have 40 millimoles. There's 2 M's there. Over, I'll put another one up there. How's that? So you get 0.307 molar. And now you know why there was a typo on the answer key, because that was where I stopped and put circle 0.31. It's like, oh, I didn't finish the problem. Okay, so now we have our H3O concentration, and so our pH is going to be equal to negative log of 0.307, and you get 0.51. Yes? Yes, yeah, because if you have strong acid and bases, the products have no acid-base properties at all. That's why there's no equilibrium, etc. Yeah. For the NaOH, how I got the 60 was I had 30 milliliters of 2 molar NaOH, so 30 times 2. Yeah. Yes. Yep. Question is if the concentration of a strong base like NaOH, is that equal to the concentration of OH minus? And the answer is yes. Well, just because it's a strong acid. Yeah, so the concentration of a strong acid grade equals the concentration of H3O plus. And the concentration of a strong base is equal to the concentration of OH. All right. Let's see. Number 9. Yes, okay. Okay, number 9 says, what is the molar solubility of barium sulfate in pure water? And so we've got a KSP there, so we know that the barium sulfate is going to be slightly soluble. So barium sulfate, so it's going to break apart into barium ions and sulfate ions there. We're going to icebox that. So we got lots of solid there, 0 barium, 0 sulfate. We say the magic words and it starts to dissolve. So we're going to lose some of our barium sulfate, some of our solid. It's going to form X amount of the barium. It's going to form X amount of the sulfate. Still going to have lots of barium sulfate, X amount of the barium, X amount of the sulfate. My KSP is equal to concentration of barium ion times concentration of sulfate ion. Okay, so I get 1.10 times 10 to the minus 10 is equal to x times x, so that's equal to x squared. So I take the square root of both sides and I get x, and that becomes equal to 1.05 times 10 to the minus 5, and we see that x, sorry, no minus there, x is equal to the concentration of barium. It's also equal to the concentration of the amount of barium sulfate that was lost, and so that's where we get the molar solubility from. So 1.05 times 10 to the minus 5. Questions at all on that? Okay. Number 10. 10's kind of a spillover from the last unit, just because every once in a while it comes up where you want to work something with a Ka or a Kb. But remember that for a conjugate pair, Ka times Kb is equal to Kw. Okay, so if gallic acid is 4.7 or 4.57 times 10 to the minus 3, that times the Kb of its conjugate is going to be equal to 1.0 times 10 to the minus 14. And when you work that one out, you get a Kb that's equal to 2.19 times 10 to the minus 12. We don't use that very often in this unit, but I know some of you just prefer to work all of your buffer stuff from a Ka standpoint, even if you're given a base. That's fine, it'll work. You just got to make sure that you do the right conversions there. All right. That's 10. 11. Okay, 11 is very similar to the problem we just did a moment ago. It's a little bit different. pH of a solution prepared by mixing 45 mils of 0.183 molar KOH and 65 mils of 0.1 molar HCl is. Okay, so once again, we have a strong acid and we have a strong base. So we're going to have KOH, our strong acid, plus HCl, our strong base. These are going to react 100%. H2O plus KCl. We really don't care about the products when it's strong acid, strong base. So again, we want to work these from the standpoint of millimoles. So for the potassium hydroxide, we do 45 times 0.183. We get 8.24. For the HCl, we have 6.5. We don't care about those. So HCl is going to run out first. So minus 6.5, minus 6.5. That's going to give us 1.74 and 0 for the HCl. Okay. So now I know my number of millimoles of KOH. So my concentration of OH minus is going to be equal to 1.74 millimoles over my new volume, which is going to be 110 milliliters because I added 65 and 45. So that comes out to be 1.58 times 10 to the minus 2. And now we just calculate a pOH by taking the negative log of that, and we get 1.80, and we just subtract that from 14, and we get a pH of 12.20. Questions on that? Okay. Number 12. Yes? Okay. So for number 12, since we're just reacting a strong acid and strong base, actually it wouldn't matter if it's strong acid, strong base, or weak acid, strong base, it doesn't matter, because we're going for neutralization, and if we're trying to neutralize something, it doesn't matter whether it's strong or weak. It's going to take the exact same volume to neutralize the amount of acid and base. So for this one, we're going to use the equation where the molarity of acid times the volume of acid is going to be equal to the molarity of base times the volume of base. And we can do that because our KOH is monobasic, so it has a single OH, and our acid, HBr, is monoprotic, which is a single H, and so they're going to react in a one-to-one. We don't have any complicated stoichiometry with that one. So for our base, or our acid rather, we've got 0.0597 molarity times the volume, which is 25 milliliters. That's got to be equal to my molarity of base. That's what we're looking for. I'm sorry, that's not what we're looking for. We know the molarity of base. It's 0.0485. What we don't know is the volume of base. And we just divide the left-hand side by 0.0485, and we get a volume of base that's equal to 30.77 milliliters, or 30.8. So neutralization calculations are usually one of the easier ones that we do. Questions on that one at all? All right, 13. I don't even know why I asked that one. I've done that one a few times today. So consider the titration of 25 milliliters of 0.2 molar benzoic acid with 0.1 molar sodium hydroxide. What is the pH when 35 milliliters of the hydroxide has been added? So here we're just doing a titration. So we don't have any equilibrium to deal with initially. We just have an acid-base reaction. Okay, so I'm going to abbreviate my benzoic acid just as HBZ for benz, plus my hydroxide. It's going to react with the OH minus part. You're welcome to include the Na. It doesn't really do anything. So that's going to go to water. The OH and the H react to form water, and it leaves me with benzoic acid's conjugate base, benzoate. Okay, so we're going to icebox that to see what is left after that titration amount. So we need to start with millimoles first. So I've got 5 millimoles of the benzoic acid, 25 times 0.2. The OH, I've got 3.5 millimoles. And then the benzoate, I've got nothing to start. So I've got fewer moles of OH minus, so that's going to run out first. So minus 3.5, minus 3.5, and then I'm going to make 3.5 of my benzoate. Now, because benzoic acid is a weak acid, that means benzoate, its conjugate, weak base, is going to have base properties, so we want to take that into account. So when I add up my I and C lines, I get 1.5 millimoles of benzoic acid left and 3.5 millimoles of benzoate that has been made. So now when I look at that, I see that I still have some of my weak acid left. I haven't neutralized it all. And I've made a good amount of its conjugate weak base. So what have I made? I've made a buffer. Okay, so that means that I can use the Henderson-Hasselbalch equation on these amounts. And so now I can just set up my pH is equal to 4.20. That's my pKa plus the log. And if you wanted to, you could go through and set up the equilibrium reaction between, or that exists with HBZ and water to show that the benzoic acid is in the reactant, so the benzoate's in the product. So that's going to give me the log of 3.5 over 1.5, and when you work all that out, you get 4.57. Questions on any part of that? Yep. Subtract the what? Well, because you mean like why the OH, not the HBZ? Well, because it's going to run out first. It has the lesser amount, so that's going to limit the reaction. Yeah.
So do you like add on to the other side unless it's a strong acid and strong base?
Right. Yeah. If you have something that has acid or base properties, you need to take that into account because that will affect the pH of the solution. Any over here? Thought I saw one over here. Okay. Good. All right. We're about halfway through and a little more than halfway through on time. Hopefully we don't run out. Number 14. Yes. Okay, so number 14 is another solubility one. Look at the concentration of iodide ions in a saturated solution of lead-2 iodide. Okay, so lead-2 iodide is going to be PbI2. It's going to be in equilibrium with lead-2 plus because it's lead-2 plus 2I minus. We're going to icebox that. Okay, so we're going to have lots of solid, no lead, no iodide to start. We're going to lose some X amount of the solid. That's going to make X amount of the lead. It's going to make 2X amount of the iodide. Okay, for every mole of the lead iodide that dissolves, I'm going to get 2 moles of iodide out because of the stoichiometry. Okay, so you got to remember that 2 there. So I'm still going to have lots of solid. I'm going to have X amount of the lead and 2X amount of the iodide. Okay, so we're going to plug that into our KSP. I'm going to go up top here. So KSP is going to be equal to the concentration of the lead ion times concentration of the I minus ion. That's going to be squared. So that's equal to X times 2X, and that 2X is squared. And my KSP here is 1.4 times 10 to the minus 8. Okay, so this over here comes out to be 4x cubed. And when I solve for x, I get a value of 1.52 times 10 to the minus 3. Okay, now we want to go back and look at the problem. The problem says, what is the concentration of iodide ions? Well, according to our icebox, iodide ions have an equilibrium concentration of 2x. So I need to take that value and multiply it by 2. And that gives me a concentration of iodide of 3.04 times 10 to the minus 3. A lot of people forgot to multiply that x by 2 because that's what the equilibrium concentration of iodide is equal to. Questions about that? You got to be really careful you don't just give an x and say woohoo and then just dump that in. It is really fun to say woohoo in the middle of the test. Number 15. Yes. Should I just do 15, 16, 17? Imagine that. You'd think I've been doing this for a while. So 15, what is the equilibrium concentration of Ag plus for that reaction? So let's just write out our reaction there. We've got silver carbonate. That's going to make 2 silvers and a carbonate ion there. We're going to icebox that. Okay, so we're going to have lots of solid to start. None of my ions, minus x, plus 2x, plus x. So I'm still going to have lots of solid in equilibrium. 2x of the silver and x of the carbonate. Okay, so our KSP is going to be equal to the concentration of silver ion. That's going to be squared times concentration of my carbonate ion. Okay, so we get 8.1 times 10 to the minus 12 is equal to 2x, and that gets squared times x, and so that's equal to 4x cubed. And when we solve that one out, we end up getting an x value of 1.265 times 10 to the minus 4. Okay, so again, that's x. Problem 15 asks for the equilibrium concentration of silver ion. We see the silver ion has an equilibrium concentration of 2x, so that means that the concentration of silver ion is going to be 2 times that, or 2.53 times 10 to the minus 4. Okay, number 16 becomes fairly simple because it just asks for the carbonate ion. And the carbonate ion is just equal to x. And so x is now equal to 1.265 times 10 to the minus 4. Okay, so that one just falls into place with 15. Any questions on either of those two? Okay, and now 17 is a little more difficult. Okay, 17 we got to kind of start all over from scratch because 17 involves a common ion, and so we've got to we're going to have an initial concentration of carbonate coming from an external source, a sodium carbonate. So we're going to set up our equilibrium reaction again. So we got Ag2 CO3 goes to 2Ag plus. It's still the same reaction. Same equilibrium exists. Set up our ice box. Still going to have lots of solid there. Going to have 0 Ag to start. But now I've got 0.020 molar of my carbonate. And that came from the concentration of the sodium carbonate that was given in the problem. So that's an initial common ion present in that solution. After that, it's the same. We're going to have minus x plus 2x plus x. This is still lots. This is 2x. This is 0.020 plus x. Okay, so now we plug that into our KSP. So we have 8.1 times 10 to the minus 12 is equal to, and that's still 2x, and that gets squared. And this is 0.020 plus x. Now we have a fairly small k there, and remember what a small k means. It means that that reaction goes very little in the forward direction. And that means x is going to be a small value. So anywhere where I'm adding or subtracting an x, we're going to just throw out that x because it's not going to affect the value of the number it's being added or subtracted to. So this becomes 8.1 times 10 to the minus 12 is equal to 4x squared times 0.020. And when we go through and we solve for x, we get a value of 1.01 times 10 to the minus 5. And again, it asks for the equilibrium concentration of silver, which is equal to 2x. And so the concentration of silver would be equal to 2x. So that's going to be turns out to be 2.01 times 10 to the minus 5. Questions there at all? Any questions? Yeah. Yes. Yeah, so that too, in the stoichiometry, factors in two places. It factors in the stoichiometry of the dissolution, and it also factors into the equilibrium constant. Yeah. All right, number 18. Yes. I haven't skipped a single problem yet, have I? All right, well, that's good. That means it wasn't too easy for problem sets. All right, so will a precipitate form if 3 times 10 to the minus 5 moles of solid Na2SO4 is added to 1 liter of 0.005 molar strontium nitrate? And we're given a KSP of strontium sulfate. Okay, so since we're looking for strontium sulfate, we're given a KSP. Let's write out the K reaction. So that's going to be solid strontium sulfate in equilibrium with the strontium ion and the sulfate ion. Just do that so we can kind of write a good KSP. So our KSP for that is going to be equal to the concentration of strontium times the concentration of sulfate. Okay, it turns out this is also going to be equal to our QSP, which is really what we need to calculate, because we don't know if we're at equilibrium or not. We have no idea where we are relative to equilibrium, so we're just calculating a Q. But remember, that's the only difference between K and Q. If you calculate a K, you know you're at equilibrium. If you calculate a Q, you have no idea. Other than that, the calculation is exactly the same. So let's calculate a Q. So we can take our strontium concentration. We have a 0.005 molar strontium nitrate solution, and so that's going to be the concentration of strontium from that solution. So 0.005 molar for the strontium, and then for the sulfate, now we're dissolving that many moles of solid Na2SO4, but it's going into a 1 liter solution, and so our concentration is going to be the same as the number of moles because we're doing 1 liter. So we would have that many moles per 1 liter. So that's our concentration of sulfate as well. So that becomes 3.0 times 10 to the minus 5. And when we work out our QSP for that, we get a value of 1.5 times 10 to the minus 7. Now we saw that our KSP, it gave it to us at 3.4 times 10 to the minus 7. So we know that the Q value is less than the K value. And what does that mean? Right, it means there will be no precipitate. It means I don't have enough products. And for a solubility problem, it means I don't have enough ions to saturate that solution, and that means there will be no precipitate. In order for there to be a precipitate, I have to have too many ions in the solution. My Q has to be greater than K, and that'll force that reaction to go in the reverse direction and make it precipitate. Okay, questions on that one at all? Does that make sense? Where are we at? There we are. 19. Yes? Addition of a common ion to a solution containing a slightly soluble ionic compound has which effect? So let's just imagine that we're dissolving something. We're just going to call it AB, and it breaks apart into A plus and B plus. Okay, so if I add that to a solution that contains, I guess it wouldn't be A plus and B plus, we'll say B minus. If we add that to a solution that says has a common ion, or we add a common ion there, that means I'm adding a source of either A plus or a source of B minus into that solution. Okay, so if we think in terms of Le Chatelier's principle, if I add some A plus, which way is that going to shift the reaction? It's going to shift it back to the left, back towards the solid. Okay, so it's going to take ions out of solution and turn it back into solid. That makes it less soluble. Same thing happens if I add B minus. If I have a common ion there, it's going to shift that reaction back towards the solid side, and it's always going to make it less soluble. So common ions always make salts less soluble. Okay, common ions do that. Questions on that one at all? All right, that was 19. How about number 20? Yeah. 20 is just another solubility problem. I want to make sure I get to some of these at the end, so I'll set this one up, but I'm not going to carry it all the way through. Okay, so we've got Ag2S. Okay, so that's going to break apart into 2 Ag plus, the sulfur 2 minus. We're just going to icebox that. I'm going to have lots of the silver sulfide, none of the silver. Apparently I was on a silver kick too, and none of the sulfide there. I'm going to lose X amount of the silver sulfide. I'm going to gain X amount of the silver, gain X amount of the sulfide. Still going to have lots of solid. 2X of the silver, X of the sulfide. Our KSP is going to be equal to 6.0 times 10 to the minus 51. So that's going to be equal to concentration of 2X. That's going to be squared for the silver times X. So that's equal to 4X cubed. Okay, so you divide by 4, take the cube root, and you're going to get an X that's equal to 1.14 times 10 to the minus 17. And it's looking for the sulfide concentration X, and so that would be the sulfide concentration. And that was 20. Good. Almost done there. We've got about 8 minutes. 21. Yeah, 21 is kind of a thought process there. It's really reading what it's asking for. So it goes back to our silver carbonate salt, which we've looked at a few times tonight. Okay, so we can imagine our silver carbonate there in an equilibrium in water. It's at some point. If I add silver to that solution, what's it going to do to the solubility? We just talked about it. If I add a common ion, what's it going to do to that solubility? It's going to decrease it. So is it more or less soluble in water than it is in the silver solution? It's more soluble in water. Okay, because when I add the silver solution, it's going to drive it back towards the solid. Okay, so A is true. What about B? Is it more soluble in water than in a solution of sodium carbonate? So if I add the carbonate ion, which way is it going to shift that reaction? It's going to shift it left. It's also going to make it less soluble because carbonate is a common ion. Adding a common ion always decreases the solubility. Okay, so it would be more soluble in water than in a solution with a common ion. And then C, is it more soluble in water than in a solution of sodium nitrate? So if I add sodium nitrate here, what effect is it going to have on the solubility? None, because sodium and nitrate aren't part of the equilibrium. Okay, they're not common, they're not anything. So it doesn't affect the solubility. So those solubilities would be the same. So the answer there would be D, A, and B are both true. Questions on that one? Okay. 22. Woo! Good. I'm glad I didn't have to do 22. 23. Okay, good. 24. We didn't talk about 24. Don't worry about that one. 25. Yes? Is that a yes? Okay. So we want to think about which of the following is a spontaneous process. We have to remember what spontaneous means. It means it does not require a continuous addition of energy in order to occur. Okay, if water freezing at 298 Kelvin, well, 298 Kelvin is 25 Celsius. Does water freeze there? No. If I want water to freeze at that temperature, I've got to start removing energy, and that takes work. Okay, it's called a freezer. How about B? A nail rusts when placed in water. Does a nail rust when you place it in water? Do you have to do anything to that nail to make it rust? No, it'll do so all on its own. Okay, so that is spontaneous. C, quite please. A flat tire inflates. Does that happen without constant addition of energy? Of course not. I really wish it did. That'd be awesome. Or how about D? A teacher's office is clean. Anything gets clean that's dirty. It takes work to clean up, doesn't it? So you have to add energy to make that happen. Yeah, if you've ever seen my office, you know that takes work, and I don't feel like doing the work. So the answer there is B. And then last one, 26. Everybody good, 26? You want to see 26? Okay. So we want a positive delta S, very similar to the problem we saw today at open class. So A has H2O gas going to H2O solid. So going from a gas to a solid, does that increase entropy? No, that goes from something very disordered to something ordered. Going from a solid and a gas to just a solid, does that increase entropy? Probably not, because we're going from 2 moles of stuff to 1 mole of stuff, and we're also going to lose all the entropy of the gas in the reactants. So that's probably a negative change in entropy. And then C, we're going from 2 moles of a liquid to 5 moles of a gas and 2 moles of a solid. That one's a little bit difficult because we've got some different phases in there, but those 5 moles of gas are really going to increase the amount of entropy there. So that would be a positive change in entropy. All right, that does it, folks. We finished right on time. I'll be in and out of my office tomorrow if you need some help. Otherwise, best of luck on the exam tomorrow. Have an amazing spring break.